which was you had to explain Coulomb's law. Well, this is not a unique way to complete the drawing. You could make it symmetrical, but decided to mark it force exerted on particle number 2. So F is the electrostatic force exerted on particle 2 by particle 1. K is a Coulomb constant. Q1 and Q2 are charges of the two particles. Q1 is the charge of the particle exerting the force. Q2 is the particle on which the force is exerted. And R is the unit vector indicating direction from particle which exerts the force toward the particle on which the force is exerted. All right. Now, I will deviate now for a moment from Gauss's law and show what to do when you cannot find electric field produced by an object or a system which doesn't have nice symmetry, so it is easy to use Gauss's law. We will return later to situations in which we can I will show more examples than just electric field produced by a single particle in which Gauss's law can be used. Well, electric field vector is a vector. So if we have a situation that a particle interacts with a lot of other particles, and we want to find out the force exerted on that particle, well, I suggested that we do it, that first we find electric field vector produced by the other particles at the location of the particle and interest, and then multiply that electric field by the charge of the particle of interest. So we can have a situation in which we want to determine at a particular location electric field produced by more than one particle. And because the force, we add force vectorially, this is how electric field became a vector as well. And obviously, electric field produced by a system of particles, how about if I make illustrated with a drawing. So let's say that I want to determine electric field at this location, but there are several particles now contributing to this field. So let's say that this particle produces a field like this one. We have another particle which produces a field like that one, and the third one which also produces electric field at this location. Now, we could find out electric fields produced by each of those locations using the law which we just derived yesterday from Coulomb's law. From Coulomb's law, we can find out what is electric field produced by individual particles. Now, let's say that if I want to find out electric field produced at this point by this particle, I will have to take Coulomb's constant, multiply it by the charge of the particle producing the field, divide by square of the distance between the point of interest and the particle, and multiply by a unit vector directed from the particle toward that point. Right? So that way I will find out this vector. I can find out this vector the same way, taking charge of the blue particle, distance from the blue particle to the point, and taking the unit vector indicating direction from that blue particle to the point of interest. And the same thing for that yellow one. And electric field at this point now is going to be a superposition of the fields produced by individual particles. So I had to add those three vectors, and I get electric field at point P. Now when a particle on which the force, we want to find force is located at point P, we take this field and multiply by the charge of that particle. Now, in case if we have a situation that there are zillions of particles, then obviously calculating in that way is too complicated. So rather than adding contributions of individual particles, we use integration, which is a different way of addition. And rather than taking charge of individual particles constituting the object, we divide object into tiny pieces. Each of those pieces can be treated like a particle, and then we can use we can use Coulomb's law. So there will be a need to relate size of a piece with the charge of a piece. For that purpose, we, as a humanity, introduce concept of charge density. And charge density is very similar to this, well, we didn't call it mass density, but we call it just density, a concept which we discussed in the past. If we wanted to find out mass of a, let's say, non-uniform object, how did we do it? We divided the object into tiny pieces. For each of those pieces, we had a relationship between the size of the piece and mass of the piece. Anybody remembers what was the relationship? If I take some kind of an object and take a tiny piece of this object, how mass of this piece is related to size of this piece, to volume more specifically. We need a function over here. Anybody?
The density?
The density, correct. We have to multiply volume by density to get mass. Now, let's say that object is not uniform, so that density varies from point to point. Which density should we take in that formula? No, function I'm asking for density, so density is, well, doesn't make sense to say that density is a function of density. However, indeed, density is a function of something. Of what? Of what?
Position.
By position of what? Of what? Position inside the object. In other words, position of the piece. So we had to take density at the location of that piece. So for example, if you calculate my density, and then if the piece is in the lung, you should take density of the lung. Right? If the piece is in the bone, then you will have to take density of the bone. Well, this concept, we can use the same approach for relating charge and size of that piece. Now, depending on the shape, actually, we relate it either to the size or to some kind of geometrical dimension. So, if we have an object which is very thin and long, we can introduce a concept referred to as linear charge density. And then, if I take a tiny piece of the object, the charge of this piece is going to be charge density multiplied by length. Now, if we want to be more unambiguous, then I would even call it linear charge density. So linear charge density relates length with of the differential segment with the charge of this differential segment. In case if we had a flat object like a surface, we can introduce concept of surface charge density, and charge of a differential segment of that sheet or flat object is going to be surface charge density multiplied by area. And the one which resembles density, mass density, is referred to as volume charge density, and volume charge density relates the time or differential volume of the object with the charge of the object. So if we have now a large object which contains zillions of particles, rather than calculating and if I want now to find out electric field at a particular location, rather than doing it particle by particle, we divide object into tiny pieces. Note actually that if this object contains zillions of particles, that piece will probably contain billions of them. But that way, we can already make calculations faster. We just have to make sure that this segment is sufficiently small compared to the distance to that considered point that it can be treated like a charged particle. Because then we can use Coulomb's law and write down the contribution from that piece using Coulomb's law. So let's now try to find out the electric field produced by this entire object. How are we going to do it? So contribution from a differential fragment from Coulomb's law is equal to Coulomb's constant, charge of the source of the field. Now we are talking about the differential field produced by differential fragment of the body, which means that dq is that differential charge of that body divided by the distance from the piece to the point of interest, and the direction is consistent with the direction from the piece toward the considered point. So this is a unit vector heading from the piece toward the point of interest. All right. So now, in order to find out electric field produced by the entire body, what do I have to do? Add them up. Correct. And if I'm adding up, I can recognize that we have a constant, so we can take out this constant in front of the integral, and this is what will be left. All the rest is inside, yeah, because now unit vector depends on this which piece we select. Distance also depends on which piece we select, and charge is the charge of the selected piece. They are not equal. They don't have to be equal. All right. I think that for the rest of this lecture, we are going now to calculate electric fields of systems of particles. And I assume actually that calculating electric field produced by few particles is relatively simple. So I will concentrate on calculating electric field of extended objects in which we have certain distribution of charge density. So we have zillions of particles. Why don't we try to find out electric field produced by a uniformly charged arc? So, well, it's a linear object, which means that linear charge density is actually independent of the piece. In general, it could be also a function of the location of that piece. And we will calculate it for a uniformly charged object. Well, so let's say that the radius of this arc is r, and in order to find electric field, we have to mentally divide that object into tiny pieces. So now, contribution from a single piece. Let's now evaluate contribution from a single piece. Note that this contribution is dependent on the piece. Let's say that the length of this piece is dl, and it is confined in that angle d theta, and well, it is at such a location that this line makes angle theta with the horizontal line. I didn't have to make a drawing exactly this way, but I decided to do it. In a moment, I'll show you a different approach, having a different drawing, and as long as you are consistent in your calculations, the solution is going to be correct. Right, let's come back to my drawing. Consistently with this drawing, let's write down what is the value of this differential electric field. Now recognize what is here. How about if we shout? K stands for? Okay. Lambda stands for charge density. dl stands for not change in length. It's differential length. I like it better. It's differential length of what? Of this considered segment. All right. What's R? Distance from? Where's the particle? Here's the particle at the origin or on the arc. Where's the particle? Arc, not origin. At this point, we have nothing at the origin. Right now, we are just calculating electric field at this location. When we calculate this electric field, we will know what will happen to another particle which we can place over there. But the problem which we are solving is to find electric field at this location of the space. So there is no particle. Now, strictly speaking, yes, so obviously, I mean, you had two choices. It was either here or there, right? Now, that differential segment, strictly speaking, is not a particle. It already contains a lot of particles. However, if this piece is sufficiently small, I can consider it to be a particle. So really, over here, this lambda dl is the charge of that segment which we consider like a particle. All right, now what is this? These are, all right, these two numbers, cosine theta and minus sine theta, are scalar components of appropriate vector. And what vector do I need there? A unit vector from the source or from the differential fragment toward the point of interest. Consult with your neighbor that indeed this is the unit vector in that direction, from the particle toward the point of interest. Talk to each other for a moment. I want everybody to see that this is indeed that unit vector. All right. Now, after this discussion, how about if I show you that with your help? from your discussion, you can shout to me what should I do. So unit vector is not marked over there. In principle, actually, I should mark it at the at this location. How about if I think it that way? Yeah. So here is, let's say that here is that segment. And I will mark that unit vector here. So consistently with the coordinate system which we have over there, I will have to copy it at the location of that fragment. So let's say that this would be x direction and this would be y direction. All right. So now, how to find out x component of that unit vector? So I will write down unit vector is equal. Now, x component of the unit vector. Well, let's start with this. What is unit vector? What do we understand by unit vector? Why is it called a unit vector? Because what? It's not length. Magnitude is 1. Right. All right. So magnitude of this vector is 1. And indeed, what Andrew said, you can think that the length of this arrow is 1. It's a unit length. All right, so what will be the length of the x component? This length is 1, so this length would be, we'll have to multiply by cosine of this angle. Right, so it will be cosine of this angle. So now we have to make sure that it is indeed the same angle as there. Can you see that? Because really, if I continue this drawing, I draw this horizontal line which you have on the slide, and on the slide, angle theta is marked there, right? Now, because these two lines are parallel, and they are crossed by the same line, then these two angles must be equal. All right, so x component, we found that x component of that unit vector is cosine theta. Now let's find y component. Well, I have to project it in this direction. Consistently with the selection of my coordinate system, of this coordinate system, I see already that it is a negative number. Right? All right, now how about length of this? So I can write down that this is minus and length of this length. Now this length, the length of that arrow was 1, so this length is going to be 1 times sine of theta. So I will have minus sine of theta. Now those students who had my lecture before are already familiar with this notation. Now if you took Physics 1 in another, somewhere else, and you stick strictly to the textbook, you probably didn't write only scalar components, but wrote it in terms of a linear combination of the unit vectors. So you would write, and it's okay. Instead of having just a pair of numbers, which you will, those of you who haven't taken Calculus 3, this is the notation which you are going to use. Because think about what are you doing with those vectors I, j, and k in those linear combinations. They are fixed. So I just abbreviated the notation. But you can think about it that such a notation, that you can represent this vector, the electric field vector, in terms of vectors I, H, and J, taking x scalar component and multiplying by vector I, and adding y scalar component multiplied by vector J, and in principle 0 and multiplied by vector K. If it is still confusing, consult it with somebody in the class who Yes, so I concentrate on scalar components of vectors rather than linear combination on the vector itself and linear combination of vectors I, j, and k. This was just a digression. We recognize that this expression represents scalar components of the differential electric field produced by a differential fragment at this particular location. Now, for a unit, let me give you a puzzle now. I'll try to confuse you. Is electric field at this location dependent on the segment along arc for a uniform charge density? Consult with each other before you answer to reinforce your opinion. Is electric field dependent? Now note that this point is a particular point. It is the center of curvature. Because this arc is a part of a circle. I selected a point which is at the center of this circle, so the distance doesn't change here. And my question is the electric field vector, differential electric field vector, dependent on the segment or not? Talk to each other. Okay? Now, let's vote. Who thinks that it is independent of the segment? Who thinks that it's dependent on the segment? Who doesn't think? All right. Well, nobody thought that it is independent of the segment. Sorry, that it is dependent of the segment. Oh, you did? You think that it is independent, and can you give us the convincing argument?
Due to the fact that each differential length would have like a symmetrical part around the center of the arc, we could use the position that would be the center of the arc.
All right. So
we wouldn't have to calculate each independent length.
So is the magnitude, are you talking now about magnitude or more about the direction of the vector? We see?
The direction of the vector.
So if we come back now to the drawing, you are saying that the direction of an electric field vector produced by this segment and by this segment is the same.
They'd be opposite around the diagonal.
Well, opposite doesn't mean that they are the same then.
If it's uniform density on the arc, then they would have the same magnitude in different directions, and then you could add those together.
Yeah, I buy that. Yeah. So what William is saying that if uniform charge density, if I divide it evenly, then magnitude of each electric field will be the same because the distance is the same, the charge is the same, and Coulomb's constant is the same. However, the unit vectors won't, right? So the directions will be different. But my question was neither about magnitude nor about the direction. My question was about the differential electric field. And William actually already almost gave an answer, yes or no. Yeah, because he figured out that, he did it correctly. Indeed, magnitude, if I take the segment over here of the same length as segment over there, both fields will have equal magnitudes. The directions won't be the same, but my question was, were the fields the same? Are the fields equal or not? So who votes that they are equal? Who votes that they are not equal? Why did you say that they are not equal?
Because the directions are the same. Like,
Because the directions are not the same. They are not equal. Now, what was equal? The magnitudes, right. You could say that the electric field strengths were equal, but not the electric fields, because electric fields are vector quantities, and two vectors are equal when they agree with magnitude and the direction. I brought it up because I know that somehow we ignore direction like it is something very unimportant. It is important. Concept of vectors was introduced in order to take care of directions. So when quantities have directional properties, we have to use vectors and distinguish vectors which are equal in magnitude but in different directions. All right, let's now come back to the calculations, because I want to solve this problem three different ways. So how about if we now find out the resultant electric field? Well, yes?
well, I'm confused by the unit vector. Like, I think it should be negative cosine and positive sine. Since, like, I don't understand why you have the positive cosine, negative sine.
Well, and actually your question is reasonable, because I did not mark the axis properly. So x direction to me is to the right. Y direction, and positive x, is to the right. So x-axis is oriented to the right. Y-axis is oriented up. Right? Now, if we come back over here and, well, concentrate at the unit vector. In Coulomb's law, we have to mark a unit vector from the source of the field toward the point of interest. Right? So, consistently with this drawing over there, it should be that way. Unit vector is that way. Like I marked it on the whiteboard. Can you see that?
So is that like DE and not the line leading to the segment? Is that
No. Coulomb's law requires not the line along the segment. It is, yeah, we have to go back to Coulomb's law. What is this unit vector? Yeah, I know that it's easy to confuse. For example, well, it's not in the same like that one. ds. Yeah, a few days ago we were using ds, which happened to be along the line. That one is from the segment toward point of interest. Do you understand that?
Yeah.
Okay. Am I clear?
Yeah, I got it now.
Okay, great. So now we have to add all contributions. And when we add, well, I have to pick up a certain variable which will identify which piece I consider. So consistently with this drawing, I thought that probably this angle will be the right variable to identify pieces. And I'm selecting, therefore, this angle theta, particularly that I see that it appears at two places in that formula as the variable of integration. So I will integrate now this expression with respect to angle theta. Well, I have dl over it because, I mean, let's see what are the variables. K is a constant. Lambda happens to be constant. Why? In general, it isn't true, but here it is because we are calculating for uniformly charged R. R happens to be constant. Why? Because point of interest is in the center of the circle, so the distance from every piece has the same value. So I can pull it out in front as well. Well, however, dl is a variable which describes now size of the segment and is inconsistent with this angle. So I have to relate it to angle d theta. Now, how the length of an arc is related with the angle on which that arc is spanned. Yeah, how length is related to angle is geometry. If we have an arc, and this angle over here is alpha, let's say radius is r, length is L. How length is related to angle? Yes, Christy, say it louder. The radius multiplied by that angle, correct. So that length over here is going to be radius of the circle multiplied by the angle on which that segment is spanned. All right, yeah, so we have now to integrate it, and we have to integrate a vector function. In other words, we have to add a lot of vectors here. Now, if we know scalar components of vector, how do we add the vectors? How to find out scalar components of the sum? We do it component by component. We add all x components, x components of all vectors, and the sum is going to be x component of the sum. We add all y components of all vectors, and we will get y component of the sum. Consult with your neighbor what I'm talking about, because although it is precisely what you should learn, I know that some of you don't comprehend what I'm saying. There are too many, I use too many sums in the expression. So, what will be x component? What do I have to add in order to get x component of vector of the resultant electric field vector? Yeah, these are constants. So I will have that, and then what do I have to integrate in order to get x component? Cosine theta, correct? Just cosine theta. This will give me x component. In order to find y component, I will have to integrate minus sine. However, now, what are the limits of integration? And why don't we refresh our memory if we want to determine, what factors do we have to consider in order to properly set the limits? What? Well, theta, but what are the limits for theta? Yeah, what are the limits for theta? And how about you? Can you say the values?
0 to 90?
From 0 to 90 degrees. Right, so if you wrote it that way, we prefer to stick with radians, so the units are consistent, so it will be from 0 to, and how many radians is 90 degrees? Pi over 2, correct. Now, what's your name?
Eric.
Eric. How Eric decided to take it from 0 to pi over 2? He subconsciously considered 3 factors. What were they?
One of them is we find theta start 0 in the diagram.
But how did he do it? What was he considering? Why, for example, not from minus pi over, not minus 2 pi to pi over 2, or how about from 0 to 5/2 pi? What would be wrong if he put, yeah, because, I mean, this piece corresponds also to angle like that. What would be wrong? Well, we have to refresh this quickly. So, when you specify the limits, you have to make sure that you account for each piece. Right? So this theta has to have such values that it points to all pieces. You have to include all pieces and nothing outside. Right? So from 0 to 5 halves pi will be including pieces which do not belong to the R. From 0 to pi over 4 will miss a lot of them. All right. Remember that when you specify the limits, you have to answer yourself those 3 questions. All right. So now the rest is so it is from 0 to pi over 2, and the rest is simple calculus 2. Now I decided to use here a famous theorem from calculus. I took indefinite integral of cosine function. I recognize that indefinite integral of cosine function is the sine function. And in the second integral, I recognize that the indefinite integral of minus sine function is cosine function. And then I plugged in the limits and got the expression for the electric field vector. What theorem did I use here? Fundamental theorem. Which one? Fundamental theorem of calculus. Which one? The first fundamental theorem of calculus. What'd you say? No, it's not the only one. We have the second fundamental theorem of calculus too. All right. So how about if we come back to another solution tomorrow? So this will be all for today. Thank you for your attention.